Students, good morning. So we'll continue nuclear chemistry class. In the previous class, you have studied nuclear transmutation reactions, is it? So now, today we'll go through the another type of nuclear reaction, that is nuclear fission reaction. Okay. So now in the nuclear fission reaction, the heavy nucleus, which when it is bombarded with a slow moving neutron, it splits into two lighter elements or two lighter nucleus of almost equal size, and with the release of huge amount of energy and also with the liberation of neutrons. Okay, so this type of reaction is said to be a nuclear fission reaction. Okay, so now we can take the same nucleus. Another mode of splitting is, say, this uranium, when it is hit with the neutron, it splits into strontium and xenon. In the previous case, the uranium splits into barium and krypton. Three neutrons are liberated and huge amount of energy is liberated. In the second equation, the mode of splitting or the new fragments formed are different, isn't it? So that means, say, the nuclear fission of the same uranium, which splits into different modes, and nearly 50 different modes of splitting of uranium are known so far. Okay, so now in each case there is a liberation of neutrons and huge amount of energy is liberated. And now in any reactions, any nuclear fission reactions, the energy liberated is equivalent to the mass defect. And in this case, in the first case, the mass defect is around 0.216 atomic mass unit. And when you multiply it by 931.5 mega electron volt, you will get nearly 200 mega electron volt energy will be liberated. Okay, so now the amount of energy liberated in different reactions will be different. That depends on the mass defect, the amount of mass which disappears during the, say, change in the nucleus. Okay, so now say the nuclear fission, okay, which are formed, that means after a nuclear fission, so the products or the daughter elements or the fragments which are formed, once again they may be radioactive in nature, and they may undergo, say, decay by emitting, say, beta particles and or neutrons, or say along with the emission of gamma radiations. Okay, so how long? Till they reach stable isotopic form or isotopic state. Okay, so now say the change, this is the nuclear fission reaction where one nucleus is hit by one neutron. So now in the reaction itself, there is a liberation of three more neutrons, and each of them are going to bombard with the available new uranium nucleus. And once again, there will be such reactions, the products will be different. And once again, in each step, there is a liberation of three more neutrons, and huge amount of energy will be liberated, and this will continue. The nuclear fission reaction will be continue, and that is said to be a nuclear chain fission reaction. It is said to be a nuclear chain fission reaction. And see, in the first step, only one neutron is bombarded. In the second step, there are three more liberated, and in the third step, nine more liberated, and all this will happen within a fraction of second. So the reaction is very fast, and it is a continuous reaction, and is a self-sustained reaction. That means energy is liberated. That energy is liberated to run the reaction. Okay, and in each step the new elements will be formed. In each step there is a number of neutrons are liberated. So okay, usually the number of neutrons liberated in nuclear fission varies from 1, 2, 3, 4, or maximum of 5 neutrons are also liberated during fission reactions. So with this we'll move on to the features, that means outlines of nuclear fission reaction. The first one we can see, in each or in any nuclear fission reaction, huge amount of energy is liberated. In the second point, we can say the nuclear fission reaction is a self-sustained chain reaction. Okay. Now the third one, we can say the amount of energy liberated. The major part of energy liberated is kinetic energy, or it is a thermal energy which can be converted into electrical energy, okay, which can be used further. And the fourth feature or the outline is, say, a good amount of energy or a part of energy will be lost in the form of gamma radiations. Okay, so this will be the outlines or the features of nuclear fission reactions. So with this we'll move on to the next one, a liquid drop model of nuclear fission reaction. So this nuclear fission reaction can be well explained with a reference to the liquid drop model. That means, say you have seen the liquid drop, which is always a spherical drop, isn't it? And the reason for this is there exist internal molecular forces, and those are responsible for surface tension. So thereby, any, say, water droplet is spherical in shape. When an external force is applied or when an energy is applied, so this becomes unstable, and the surface tension forces will be disturbed or destroyed, and it changes into elliptical form or ellipsoidal form, and further it changes into dumbbell shape, and later it breaks or splits into two almost equal parts with the liberation of, say, okay, into two parts. This is with respect to liquid drop. In the same way, one can explain the splitting of uranium into parts, into its, say, daughter elements. For example, uranium, when it is bombarded with, say, the neutron, that neutron, or after bombarding, it supplies an energy, okay, to the nucleus of nucleus of uranium. When the uranium is bombarded with a neutron, so it gets energy, it becomes a compound nucleus which is very unstable, highly energetic. Okay, that extra energy which enters or causes this nucleus to set in a series of rapid oscillations. So it starts oscillating. As a result, it changes into ellipsoidal form, and further it changes into dumbbell shape, and further it breaks into two halves or into daughter elements, and with the liberation of neutrons as well as huge amount of energy. So okay, this is the basic principle which can be compared with the breaking of, splitting of water droplets or liquid droplets, and therefore it is said to be the splitting of heavy nucleus into lighter nucleus can be explained with the help of liquid drop model. Okay, so now with this we'll move on to the next one, that is nuclear reactor. Okay, nuclear reactor is a device. Nuclear reactor is a device which controls the fission chain reaction, and the liberated energy is utilized for the peaceful purposes. Okay, so now the nuclear reactor where the liberated energy is utilized for the peaceful purposes is said to be a power generator, or it is a nuclear power generator. Okay, so now in a nuclear reactor, a controlled fission of uranium 235 or plutonium 230, plutonium 239. So this will be used as a fuel. Uranium 235 or uranium 238 or plutonium 239. So these are the heavy unstable nuclei or the elements which are used in nuclear reactors. Okay, now in the nuclear reactors, the same type of reaction takes place. In each step, there is a liberation of say huge amount of energy which helps in sustaining the reaction, and at the same time the initiators, that means neutrons, are liberated, and those neutrons are going to hit or going to bombard with the new heavy nucleus, for example new uranium atoms which are present in the reactor, and thereby the reaction will continue, and that reaction is said to be a chain reaction. It is a nuclear fission chain reaction. Okay, so for example, if you refer this one, it is with respect to only the neutrons. Say the single neutron, when it hits the uranium, so there is a liberation of 3 neutrons, and once again that will hit with other 3 uranium atoms, and once again there is a nuclear reaction, this type of splitting reaction. And here such, say the daughter elements are not shown, and this is only with respect to neutrons, and this will continue. Say large number of neutrons are produced within a very short fraction of say time or fraction of second. Okay, so now say the energy liberated can be controlled or can be controlled, or the reaction chain, that means this fission chain reaction can be controlled in nuclear reactor, thereby the liberated energy can be utilized for the useful purposes. Okay, so now here there is one factor K. So it is a critical factor where it is related with the number of neutrons produced per fission to the number of neutrons producing fission. Okay, here the number of neutrons produced, it may be 3, 4 or 1, 2, so like this, and here the number of producing fission. Okay, so each neutron is going to react. So this ratio, if it is equal to 1, then that reaction, fission reaction, is said to be a controlled chain fission reaction. If K is less than 1, then the chain reaction cannot be sustained, and if it is greater than 1, it is a uncontrolled chain reaction, uncontrolled fission reaction. Okay, so with this we'll move on to the next about the nuclear reactors, further parts of nuclear reactors, and how to control the nuclear fission reactions in nuclear reactors. So that means about the parts of nuclear reactors and their purpose or their job. So in conducting or in controlling, so such fission chain reactions are studied in the next class. Okay, thank you.